thank you. I don't use mic because my voice is loud enough. Okay. Okay, so I'm going to present this paper. So I did this talk last year, same in other conference. So this paper has been appeared in Science Journal Optimization. So to appear is wrong, but anyway. So this is joint work with my postdoc supervisor. This is done when I'm a postdoc in University of Waterloo Optimization Department, and with Hans de Stack and Steve Barbasis. So what the heck is this? Okay, this is very ugly. Okay, I'm going to explain what the heck it is. Don't worry, the idea is very easy to understand. So this is just to scare people, okay? So what the heck does it mean? Many subscript, many superscripts, and then I have subscript of subscript, I have subscript of subscript of subscript, which is... Okay, first, very important to know, the level here is not a bi-level optimization. It's different from what you may know is bi-level. The level here comes from the multi-grid level. I will explain, don't worry. So very simple, no big deal. So I will simplify everything using just two symbols called big and small. So what does it mean? I will explain now. So what the heck? Okay, classical setup. Okay, the two speakers before me are talking the same thing, so you should be very familiar. So what the heck is it? F differentiable, G not differentiable. That's it. Of course, both of them convex because this is classical standard. And why F is differentiable, data fitting or distant to some data set. G is not differentiable, regularizer, non-smooth, blah blah blah, lot of things. So these are classical. Okay. Everything in finite dimensional space, I have to talk about it because I am going to use infinite dimensional space technique. And then I don't care about randomness. There's no second order thing, no linear thing, no big sum. And I'm not talking about application much because mostly it's called non-smooth analysis. Okay, these are just technical terms. Okay, so now let's go to the big idea. What's the idea? Very, very simple. We want to solve this. So now I have the same expression, minimize F and G. I have a big here. What does big mean? For example, galaxy image. So the similar idea has been used by this French group in France that they try to what? Image the space, the universe. Okay, you know, universe, black hole image, many hard disks, too expensive to compute even in a small computer. Okay, then what? Then the problem is just too big. What's the classical trick? Stochastic gradient. And I'm not a fan of randomness, so I'm going to do something else. So what's that? Make something smaller. What does small mean? Small means this is your original problem. Your original problem is minimize f big plus g big on variable x big. What you do? You make something f small plus g small on the variable x small. Immediately you have three questions. What does small mean? Define small, number one. Number two, how do you form a small problem? And number three, why is it useful? So this is the idea. Okay? This idea is very old. Okay, I can tell you, this idea is definitely not by me. This idea most likely comes from PDE. It's called multigrid in 1962 by Russia. Okay? And then what? Well, probably if you talk about purely it's a geometric idea, then it comes from even earlier. Okay? So what's that? This picture gives you the idea. Suppose you have originally have the picture in the below. I call it level 0. 0 means the original. And then what do? You make a level 1. This is what I mean level. It's not a bi-level thing. It means I make something smaller, and then I work on it. And then what? I can keep making it smaller, and then I work on it, and I keep making it smaller, 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 until I reach just one variable. It's still a picture, right? Although that does not tell us anything, but still, it's a picture. The idea is very simple. If you can gain something on level 4, when you solve level 3, you speed up. If you can gain something from level 3 to solve level 2, you speed up. Or if you can gain something from level 0 by solving only level 4, you speed up. That's the idea. Okay? So, what's the difference here from the other technique? Stochastic gradient descent, you have noise, you have randomness, you have crazy variance bound, not my cup of tea. This one, everything is deterministic and you can actually know what is happening. There's some assumption, of course, you need to know, but that's a technical detail. So this is just a classical approach. You make something smaller, you sacrifice accuracy, but you make sure the area is correct, is bounded, and then you work on a small problem because it's smaller, it's cheaper to do, then you gain some speed up. Okay, and this has been used in many areas in computational mathematics. Even nowadays in deep learning or large language model, they call it distillation. It's just fancy name. It's just the same idea. Okay. So what's the technicality here? So this comes from PDE called multigrid. It's a whole area of research. Okay. And what's the new thing here? I'm going to extend what is somewhat called FAS, full approximation scheme, to non-smooth optimization. That's the idea. Because PDE, okay, you have the word D, that means everything is differentiable. Now I'm going to talk about how to make this to non-differentiable cases. Okay? And focus is FAS. And actually, as I said, this idea exists 100 years ago. So of course there are people in PDE have the same idea when they want to work on optimization, but they are doing this. What is this? You have an absolute value, and then you consider absolute value as square root of x squared plus a small number. Now you smooth everything. Now of course you can make a small problem. But what I'm going to do is I work directly on the non-differentiable thing and try to make it small. Okay, that's the idea. So that means no smoothing, face sub-differential directly, look at the hardest thing and then work over it. And what is the main output? Very simple, is to show that multigrid coming from PDE, which assume everything is differentiable, also works in non-differentiable case. Okay, and of course you have a bunch of rate. Okay, I have 3 convergence rate, but I'm not going to show you the detail. So how do you perform the procedure? This is the detail. What's the detail? So you have a big and small, right? So this is the idea. You consider your function big, compose it with an operator called R. R is called restriction. This is come from PDE. So you then get something called small. So that means small is just my function f composed it with an R. This is abstract in the sense that I didn't specify what is R. Okay? And then what? So if I write it explicitly, what is f small x small? It's just function big on something I call it x small. So in other words, if I have an R, a magic R, that somehow, now I don't need to put an x back here, but I can replace it by a smaller vector. But I keep everything. Then, good. Then, of course, there's a problem. What the heck is this R? Is this how black magic? Okay, of course not. The whole PDE people, they spend their whole life on studying how to make this R. Okay? So, R is, for example, you can see as a matrix. In general, I said this is an abstract expression. R can be not a matrix, can be something else. But here, make it simple. Consider this is a matrix. Okay, then, for example, let's say R is random. You have random subspace. And if R is some column of identity matrix, you have coordinate descent. And if R comes from PDE, you have multigrid. So in other words, this whole framework subsumes all these 3 methods. Okay, no free lunch, of course. What's the no free lunch? That means you sacrifice something, right? The sacrification is, how do you know R? Actually, knowing how to find R is an open problem even for the PD people. So, I'm cheating by using known R. So that is, if, for example, you have a biology problem, you have some cancer image, you ask me, what's the R? Okay, I can tell you there exists such R, but do I know it? I don't know. And it will be a PhD student project, okay? So here's now the math thing, okay, the mathematics. So now, red are the new thing. The thing in black are not new. So the original PDE people are working on minimizing some f, okay? Now I plus some non-differentiable thing here. Okay, and of course I will do proximal gradient descent. That is, after I do the gradient descent step, I perform smoothing, so-called Moro envelope. This actually is the key part that makes the multigrid works. And I have this, and now I iterate, I don't quite xk plus 1, I quite k plus half because I'm going to do a lot of things here. Then now I'm going to make a smaller version of my x by using R. What's R? Assume we know R for a moment. So if I multiply x big by R, I get something smaller. Okay? And then because I have R, what's the small f? It's the composition of my big F with the R. And similarly, is the composition of big G with my R give me small g. Okay, and what's new is that this R is new. Okay, because I want to make sure it also fits non-differentiable thing. Now this part is what the fuck? Okay, so what that? I have this thing. What the heck is it? Oh my gosh! So I have F plus G. So I have F plus G and F plus G. Okay, these are big. These are big. So everything here is big. These are small. These are small. Everything here are small. You cannot add two things from different dimensions. You cannot add a two-dimensional vector to a five-dimensional vector. So you need to connect them by the R. So that means this R will make everything big to a smaller size so that I can add them up. Number one. Number two, this is subdifferential. That means slope, but for non-differentiable generalization. So this actually is a set. This is also a set. So this is not more normal at distance subtraction. This is Minkowski subtraction. Okay, so these are set plus set, and therefore it's not equal but belong to because it's set. Now what I do after I have this funny tau, I do a same thing here but add it inside the slope. So what the heck is it? You can think of this tau is what? Look at this. If you are good at convex analysis, you know the optimality condition of an optimization problem if 0 belongs to the subdifferential. So this is something like what? The subdifferential difference between small rho and big rho, so something like residual. That means how much you are away from not being optimal. And now I add that here, it's like a correction. And I do a proximal gradient step in the same form. Lastly, I have what? I have something obtained for the small world, but all I want is the big world. So I add my small world here after the update under the influence of my big world, and then what? Add it back to this one coming from here. Okay, blue is blue. Okay, this gives me a direction. And this direction, I make it back to the big world by doing the P called prolongation, just basically opposite of R. So now this is in big world. And then there's an alpha, just think of it as 1 for simplicity. I add it to big X. Then this is now my X k plus 1. So this is the whole idea. What is the overall idea? You have your original algorithm. Okay, and then you do 2, 3, 4, which somehow magically give you a new update direction like this, and it works. Okay, so what are the funny things? So this is a funny thing. Subdifferential can be empty set. If you add 3 to empty set, you get empty set. Anything touching empty set become empty set. Empty set is black hole in mathematics. So there will be some detail on how to avoid this guy being empty sets. These are details. So we need to make sure empty set never appear. Number 2, this is a belong to. That means it's selection problem. You select among all the possible difference of subgradient in 2 sets. Then the question is how. This is same as parameter tuning or line search. I'm going to show you. We don't care. You can take whatever you want, always work. So it's a global method. That means whatever tau you choose, it works. Lastly, this is the new update, right? Your big variable plus something. Is this a working direction? Yes, we show that this also works. Lastly, there's an alpha there. Does this alpha exist? What happens if this alpha is 0? No, we show that this alpha exists. That's the contribution. So what's the new thing? So first, this is the most crazy expression in the whole slide. So this is the Minkowski sum between 2 subdifferential. Okay, now I'm going to break it. So because of Moro-Rockefeller theorem, which basically means you can split subdifferential into each of them. So now we have set plus set, and here is set plus set. Okay, and because I assume every differentiable, so this is singleton, this is singleton, reduced to classical gradient. So I have this. Easy. And now what? This is singleton, this is singleton. I group them here. This is just singleton. The simple part, no big deal. And this is classical. The crazy part is these 2 things. This is Minkowski sum of 2 things. Okay, for simplicity, I put the R next to the negative sign, so now the R is negative. So I can only write the plus, I don't need to write the crazy circle minus, okay? So this is a subdifferential of small world, this is subdifferential of big world, and then map it to small world, set and a set, this is the hard part. So what we do is, these two addition actually is the hard part, is the most theoretically challenging part. What I do is I basically make this from Minkowski sum to set addition of one element by making sure that as long as this thing is a singleton, then I don't need to worry about the craziness of Minkowski sum. So what's the new thing here? The new thing here is this plus now becomes the normal plus. In other words, this thing is not a set, it's one element. And this is set, right? So actually I design a funny R that I don't care what is this. It will always collapse to just single point. And that's the new thing. So this is the thing. What's the open problem? The open problem, that means continuation of this research, if you are interested, is work on this instead of this. Yes, the open problem, okay? And you now can see this new thing doesn't exist in literature. Of course, I argue with the reviewer in the Science Journal Optimization, and of course, in the end, they agree, yeah, this is new, okay? And then what the heck is this tau thing? This tau thing is the linkage between the big world and small world. That means what? So, this is a theorem. If I solve the big problem, then I solve the small problem. So, don't forget, R means make something big to small, so this means small. Small of what? The small version of my big solution. Here's important. This is saying this solve this. I'm not saying this solves small if I make it small. I'm solving this solves small plus something. This is a residual between the subdifferential. So, in other words, proximal gradient conversion in big world implies proximal gradient conversion in small world, but each model is a perturbed small world, not small world. I'm not saying big soft big implies small, small, soft, small. I'm saying big, soft, big implies small, soft, perturbed, small. And if this guy disappears, I get small solution. Something like that, okay? Okay, then how do you prove this? Just detail, read the paper, okay? And then now, second thing, I have this step in the algorithm. So what the heck is this? Let me go back to the big picture. Is this step number 4? No, number 5, okay? I have a big plus the contribution from the small. Okay, this is the 5. So, therefore, I need to say this thing is working. This thing is working by showing this funny thing is a direction always have a negative angle with the subgradient for whatever subgradient you choose here. So, in other words, this is not one inequality, this is infinitely many inequality, because this is a set. And I show that this is true for whatever subgradient you give me. Okay? And this holds for what? Don't forget, this thing the small thing comes from what? Comes from solving this thing. And you have a tau, and tau link back to the big world, and tau is also coming from a set. And I'm saying this is true for whatever subgradient and also whatever tau you give me. That's the funny part, okay? And also the hard part, okay? Read the paper for the detail if you are interested. And then what? I need to show the step size exists. This part, in my opinion, the proof is so elegant. I like it. So how do I prove this number exists? I prove this number exists, I need to show that if I do this, now my new variable is smaller than my old variable and strictly decreasing. And here's the idea. So if I have this is exactly this line, then what? This is what? Half space. Because this is basically saying I have an inner product. This is a hyperplane. This is a set. If this is strictly smaller than 0, that means if I have a normal that is defined as this expression, is a half space of this set. Subdifferential is a compact set. That means you always have strict separation, and that strict separation means you have a positive distance here. In other words, what does it mean? Okay, this is hard to visualize. Imagine this whole expression is a box. This box is my subdifferential. Okay, now I'm saying I have a hyperplane. Let's assume this line of text is a straight line. I'm saying there's always a gap between this box and my line. And this gap is exactly the directional derivative in the non-differentiable case. So therefore, there exists a step size alpha that I can go down, regardless of what subdifferential I do and what tau I choose and what are the parameters I chose previously. And that will be good. But the reason why I do all this is because I don't like to tune parameters. That's it, okay? Does not mean you cannot do line search, you can. But actually in the paper, I discussed that this problem, tuning alpha, is extremely difficult because this is what? Number one, tuning alpha, that means you do line search. Let's say you do Armijou rule. That means you need to satisfy some angle condition and then something sufficiently decrease, that kind of thing. The problem is that condition does not hold here because this is a subdifferential. That means the Armijou rule, which is for smooth problem, does not work on non-smooth problem. There will be some technical challenge. And then if you look into the literature on searching of step size on non-differentiable problem but convex, it's a mess. So, no. Okay, so therefore, that's why this is deep. And what's the bad thing? The sad news. This actually is sad news. Because I don't do line search, so I have what? Something smaller than 0. I don't have something smaller than some number. I just show it smaller than 0. I didn't show my function value must go down some amount. This is because I don't do line search. Okay, but if you want to show that, you need to show the line search for non-smooth problem. It's a mess, so that's why I don't have that. But anyway, so now this is all the theory result. What's the theory result? Here is the theory result. Number one, I proved the fixed point convergence. That means if big world converge, small world converge. If small world converge, big world converge. And then the angle condition, I don't care what subgradient, this is always true. Number three, I have descent, that means going down, and step size exists. And then I have rate 1, rate 2, rate 3, okay, and also a convergence of the sequence of x. Yes? And then, why just 2 level? Why not go to 3 level, 4 level, 5 level, 6 level? So this is the beauty. If your original problem have n variable, I do this 5 times. I reduce my problem size by 1,000. Divide by 1,000. And then everything can be solved. And how expensive it is? It's just simple math. It's at most 2.7 times, so it's good, fast. Okay, blah blah blah, no point tell you, okay, how fast? Very fast. You need this number of iteration, I only need 50. You need this number of time, I only need this number of time. Accuracy is better, okay, faster than this problem, so here, right? Okay, this is the end. Okay.
You have done, if you want to comment more on the last slide.
Okay, so let me give you an example. So what's the example here? Is that first let me tell you, is this possible to do this for imaging problem? Yes. The space image I show you in the very beginning exactly is the same thing like this done in the space image by the French group. So they do the same thing, slightly different on the setting on the space image. But what about this? This is a specially designed problem to show something. Okay, number one, I said we need to know the R. So this actually comes from PDE equal elastic optical problem or free boundary problem that people know what's the R. So that means I can cheat. Okay, don't forget there's a no free lunch. I'm saying this looks very well, very fast, super good, but there's a trade-off. You need to know the R. Okay, this problem people know R. But more importantly, this problem has an important thing. This problem is strongly convex and smooth at the same time, but strong convexity goes to 0 very quickly, and smooth constant is unknown. So that means this kind of problem, you are forced to do line search for the mu and L. And as I said, I don't care about parameter, and it still works faster. That means if I do line search, it can be even more faster. And what are these examples? So black is the classic cogradient descent in the proximal version. That means everybody will beat it. And then Vista is deep blue. Vista with restart is this one. Very good actually, but then somehow stuck. And then this is a method also on multigrid, but some not the same. And lastly, the green is my method. That's the new thing. And you can see, if I touch machine precision, I need, let's say, 20 seconds. And all of them almost never. Okay, this looks like it touched, but you know, networks have a ripple that actually it never touched. So therefore, I touch at 20 something, and then they converge forever. Okay, that's it. So this paper is not to appear, it's published. Okay, so these are all news. And then what are the key points to take home? Is that, so basically is that, the idea is my first picture. So I think nowadays people do AI very big. This is very worthy to do. People know, you just use 1 million variable, 1 million data point. But in my opinion, if you put 1 million data point, if there are 2,000 within them, they are contrasted with each other, you are stupid. So this is the idea. How do you select a good data, subset data, and then perform the task, make it faster? I think this is the general trend. Yeah, that's the idea. So this is the idea, and then that's it. The last line is wrong anymore. No more. Okay, finish.